Our next speaker is Cristobal Young, and he is an assistant professor of sociology at Stanford University. He works in the overlapping fields of economic sociology, stratification, and statistical methods. He studies social policies that affect income inequality, ranging from millionaire taxes to unemployment insurance. His methodological research focuses on model uncertainty and robust results.
Hey everyone. Okay, so I wanted to start out today by taking a bit of a step back and thinking about transparency in the history of science, particularly at the dawn of the scientific revolution. So the Royal Society was founded in 1660. It's Britain's Academy of Science. It's the oldest scientific body still in existence, and its founding principle and motto and mantra is nihilus in verba. Roughly translated as take no one's word for it, or see for yourself. So in the history of science, replication was really the foundation of discovery. When a scientist discovered something about, the properties of light or magnetism or the circulation of blood or objects in the solar system, the task was to really explain to other scientists exactly how to replicate this work so that other scientists could observe the same evidence and be persuaded by their own eyes. Scientific revolution emerged from a world of superstition and dogma and mystics and prophets, and scientists needed to separate themselves from the age of dogma and superstition. So people like Sir Francis Bacon laid out central tenets of the scientific method, which was sort of methods of thinking, skepticism, observation, so forth, but science really had to be communicated as well, and it had to be more convincing than superstition. So how could we know that the insights from science actually derived from the scientific method? For science to become a knowledge that accumulated and could build on itself, it needed the principle of replication. Follow these methods and see for yourself. So the Royal Society's new scientific journal, first issue, first article, career-making paper by young Isaac Newton. Any history of science buffs out there know where Isaac Newton, greatest scientist of all time, sort of started? And again, don't say gravity, but okay, it's kind of surprising. The theory of color. He was working on color, and he told us really extraordinary, almost magical things. We thought that natural light, the light from the sun or from these light bulbs here, was just colorless. It was just white light, and that things had color. That trees are green, snow is white, autumn leaves are yellow and red. But Newton demonstrated that none of this is true. Pure white light is actually an aggregate of many different rays of light. We would call them today wavelengths. These rays of light all have different color, and when we look out at the world and see color, it's really just because different things tend to reflect and refract light to us in different ways. Color is not in things, color is in light itself. So this was a really shocking reversal of our sort of everyday perception, sensory perception of the world, that things don't have light. Things don't have color, only light has color. Why should we believe any of this? How is this different from superstition or stories of dragons in foreign lands? Science and magic can be hard to distinguish. So Newton spent most of his article explaining the exact details of his experiments using prisms to decompose and recombine rays of light. You start here with this white light, and you can decompose this. And some people thought, well, maybe there's just something weird in this prism. Well, he showed that you can start with the white light, you can decompose it into the rays, and you can run it through another prism, turn it back into white light, and then decompose that again. Very compelling stuff. So the experiments took genius to conceive, but anyone with means could replicate them. And his goal was just to show people how to manipulate light so others can see the true property of light for themselves. Early science had to fight for truth in a world of superstition and dogma, and science had no authority to rest on. Early scientists like Newton and his colleagues at the Royal Society desperately wanted their work to be replicated. This was sort of the central foundation of scientific of the scientific revolution, and it was central to distinguishing science from dogma. To have one's work replicated was an accomplishment in and of itself because it was truly to enter the discourse of science. But today, replication has really fallen from grace, from the sort of highest idealism of the scientific revolution. Replication, has become a bit of a backwater in science. It's sort of low-status grunt work. It's merely confirming the intelligence of other people, or maybe it's an attack on another scholar, challenging their competence and integrity, and risking feuds that diminish everyone's credibility. So there's a massive volume of work published each year, but only a tiny number of replications. For any given article, it's a reasonable assumption if you produce an article that nobody's going to replicate it, and nobody will ever see for themselves how the evidence was created. And we've come to prefer this way of modern science, in fact. So ironically, there's never been a time in history when technology has been so supportive of the Royal Society's sort of mantra of see for yourself. In early computing, these are some of the ways that we ran our analyses. So 1920s and 30s, this was an era when computers were human. It was an occupational category. So you could say, hi, my name's Cristobal, I'm a computer. For moderate-sized data, running one OLS regression was an accomplishment of both capital and labor. And this shows, just rooms filled with people working with computing machines would calculate sums of squares. And, in this day, there was no code to share, and the cost of rerunning the analysis was extraordinary, prohibitive. Fast forward a bit to the 1970s, here we're in an era of timeshare mainframe computers. So you would turn your data and code into a box of punch cards, put it into a queue that would go into the shared mainframe, and maybe have results 5 days later. Often the result was, there was a bug in your code and the program crashed. So not an era when we're running a lot of regressions, and sharing was very hard. So asking people to share their data would be saying, create a new box of punch cards by hand for me and then mail them across the country. It virtually didn't happen. But things are very different today, and with online connectivity and massive computational power, the data can be downloaded just as easily as a PDF of an article. Once the data and code have been prepared, it's costless to distribute, just like it's costless to distribute the article itself. Second, computational power means that running the code is essentially trivial in terms of cost. And this means we don't have to make so many assumptions about the best way to do an analysis. So if somebody thinks that you've miscoded a variable or used the wrong regression command, it's very easy for you or for them to just tweak the code and rerun the entire analysis. And so the computational cost of alternative modeling choices today is very low. Computationally, it's essentially zero. So very easy to distribute data and code along with an article, very easy to run alternative models. Readers can see an analysis for themselves in a way that was never possible in the past. And for scientists, this is both exciting and intimidating. So this is a forthcoming paper I have in Sociological Methods and Research, Model Uncertainty and Robustness. The point is, here's my replication package. So if you just copy and paste this command, this line into Stata, that's supposed to be one line. If you do this thing, this tells you where to go find my replication file. The replication file will then tell your computer to download my Stata software. It'll tell your computer to download the data sets I use, and it'll rerun all the analysis in the paper. And it'll run probably faster from beginning to end than you'll be able to read the abstract of the article. Okay, but few sociologists are willing or able to provide replications like this. So, small field experiment conducted by my students as part of a graduate course in statistical methods. I asked students to select sociology articles that they admired, they wanted to learn from, and then to go off and ask the authors for a replication package. And out of the 53 sociologists contacted, only 15 authors, 28%, provided a replication package. So, this is a small N study, but I think it's illustrative of the state of open source social science in my discipline today. Here's some of the responses that my students received from authors. Here's the data file and stata do file to reproduce the tables. Let me know if you have any questions. Attached are the data and R code that does all the regression models in the paper. Assuming that you know R, you can literally redo the entire paper in a few minutes. So same kind of thing, super open. But, you know, many of the responses were more like, well, I applaud your efforts to replicate my research. The best guidance I can offer is that the details about the data and the analysis strategies are in the paper. My favorite. I don't keep or produce replication packages. Data takes a significant amount of human capital and financial resources and serves as a barrier to entry against other researchers. They can do it themselves. So instead of nullius in verbis, see for yourself, it's more like do it yourself, right? So people, I think, are anxious about replication packages because they're fearful that someone will find an error in their work and then they'll be publicly humiliated or accused of academic fraud. People often feel a little bit insecure about their standing as a scientist, and it's certainly easy to make mistakes in statistical analysis, and it's a rivalrous world out there. So people often see their data and code as their private property as well. So they spend months and years developing their code for their analysis, and then many authors are very reluctant to just give away their code to a potential competitor or a potential rival. So this study the sort of mini study, I posted it just on a sociology blog, get some people's reaction. There were ferocious reactions. One senior professor commented, yeah, read the goddamn paper yourself and figure it out is not an unreasonable response. The lazy person who used the available codes is only going to find the same stuff that the original author found. And many people were signing on and saying, yeah, he makes a good point, you know. But some responses were like, well, not having a replication package was maybe fine in the 1990s, but now it's really a sign of someone who's more slob than scientist and whose work should be evaluated accordingly. So, you know, the tension is running pretty high on this blog at this point. And then finally, Gary King from Political Science stepped in and just said, why don't you just publish the list of these people who wouldn't release their code, you know? And people were all of a sudden extremely worried that I was going to do this. And I was hearing from people who were like, we released our code, right? So by the end of the day, people are very, very concerned about not seeming to be transparent in their work, and I think this is a good thing. A lot of the resistance, ultimately, to replication packages, I think, is a problem of collective action. You know, if we all share our code, a lot of these reasons go away, you know. We'll all understand everyone's work more fully. We'll all learn more about how research is actually being done. We'll all gain more insight into how research can be improved. All of our work will be better, more reliable, more persuasive. Replication packages are public goods. But if just one person is sharing their code, others can free ride on their hard work. It will empower their critics. And they can lose the competitive advantage that comes from really investing in hard data sets and specialized knowledge and methods. So for an individual, sharing code really only makes sense when most other researchers are doing it, when sharing your code grants you membership into a community of scholars who reciprocally share their code back, and when refusing to share code sort of excludes you from the scientific community. So until then, providing replication packages, I think, will be a genuine dilemma for scholars. Okay, so there's a second aspect of transparency that I wanted to talk about. So computational power, as I was saying, makes running statistical models very easy. So we spend a lot of time doing it. But computational power hasn't changed the amount of page space that we have for reporting research results in articles. It hasn't changed reader attention span for how long an article can be. So it's created a lot of asymmetry between author and reader today. In the course of developing a research paper, authors can and do run hundreds or thousands of different statistical models on their data. But journal space hasn't changed much, so we still have room for only publishing a handful of the resulting estimates. So in the early days, let's see, I lost some slides here. That's too bad, they were kind of nice. But anyway, in the early days, limits on computational power really created a veil of ignorance in which neither the analyst nor the reader knew much about what alternative statistical models would find. Like, there was always other ways to do an analysis, but computation was so difficult that people really just figured out their one most plausible, most defensible method and only ran that and just published that one thing. The other possibilities were known to no one. But today that veil has been lifted for analysts who can run thousands of models, but it has not been lifted for readers who can still only read the published tables. And so gradually this has been creating a sort of growing problem of asymmetric information between analyst and reader, between author and reader. Authors know a lot more about how sensitive the results are than do the readers. So, at least in my field, I think this is the biggest reason why researchers are skeptical of other people's research. They think the analysis could just easily turn out differently if someone else did it. And I think this is at least half the reason why authors are anxious about providing replication packages. They fear that the skeptics might be right. So why do people want replication packages? What is it exactly that scientists want to see for themselves? You know, on the one hand, they want to see the data, they want to know more about how the analysis was done, but more importantly, I think replication is really about, they want to question the analysis. And the deeper issue is not about exact replication, but what happens when you do the analysis a little bit differently. So, a lot of modeling choices go into an analysis. I'll just run through it. So Ed Leamer, famous guy, wrote a paper called "Let's Take the Con Out of Econometrics." So he describes the process of model specification. Sometimes I take the error terms to be correlated, sometimes uncorrelated. Sometimes I include observations from the decade of the 50s, sometimes I exclude them. Sometimes the equation is linear, sometimes nonlinear. Sometimes I control for variable z, sometimes I don't. And this is the sort of things that we're talking about. And how influential are any of these decisions? Does the results hang on any of these choices? So this is something that I've been working on in the paper that I showed you earlier, model robustness. There's three basic elements of model specification. We can think of choice of control variables, choice of key variable definitions. So, you know, if we're measuring social capital, do we measure that as voter turnout or as volunteer activity? Is religiosity, does that mean church attendance or belief in God? These kinds of things. There's a lot of these choices that we need to make. And then finally, choice of functional form, and there's a lot of different possible options here and a lot of different ways to run analyses, some of which are data specific, but some are not. So, model assumptions are necessary. You know, point estimates can't be calculated until you've made choices about these kinds of things. It's just, you know, we have to make these choices, and we often have to suppress tangible uncertainty about what's the best way to do it so that we can actually calculate an estimate. But model assumptions can also be relaxed. So we can think about defining a model space of all sort of plausible models, defined as sort of possible combinations of reasonable elements of model decision making. So we can think of a case where we've got 12 plausible controls. We're not sure they absolutely have to be there, but they seem reasonable. Okay, we can think of 3 plausible definitions of, say, an outcome variable, and we could have 4 sort of plausible functional forms, OLS, Poisson, and so forth. If you take these all in combination, if you take all possible combinations of these ingredients, it yields 32,768 possible models that you could run. Okay, so let's get a sense of what it would look like if you do this. As I say, with computation these days, it doesn't take you very long to run 32,000 models. You know, depending on the complexity of the data and the size, maybe it would take an hour. Okay, so just quickly, couple of empirical examples. Union wage premium. Do union members earn more? I don't know if you can see this, and I don't really see a pointer on this thing, but the top line indicates that union members have about 11% wage premium over non-union members. And there's, as you can see, a bunch of control variables. How robust is this to any specific item or ingredient in the model? Okay, so we've got 10 possible controls. This gives us 1,000 unique combinations of the control variables. If we run them, we get this distribution that's actually a really nice normal distribution. The estimates range from about, about a 10% wage premium to about a 20% wage premium. Very consistent, and we can look at, 100% sign stability and 100% significant rate. So with these sort of model ingredients, there's no way to run this analysis other than to get a significant positive union wage premium. In other cases, though, we'll be in a more ambiguous world. This is a mortgage lending study, the effect of gender on mortgage lending. I'm really running out of time, so I'll just give you the impressionistic. This result suggests that banks are actually more likely to lend to women than men, but it's ambiguous. Only 25% significance rate. And this is what the distribution looks like. There's clusters of estimates around 0, around 2.5%, around 4.5%. So the data itself aren't telling us the answer. We have to make analytical choices. And I'd love to tell you a bit more about this, but in the interest of time, we can also think, last empirical example of tax migration. Do people move from high tax to low tax states? You can run a few models showing that, there seems like some robust evidence. There's this top estimate here. You put in some sensible controls. You can even try it out with different sources of data. But it turns out that this is a real knife-edge specification that holds only in about 1 in 100 models. So here we've got 12 possible controls, 2 possible different data sets, IRS data, census data, 3 possible estimation commands, OLS, Poisson, negative binomial, 25,000 models basically. This is a distribution. This is the estimate we saw before. It's in the extreme tail. The distribution of all these estimates, this is 25,000 estimates, is really tightly centered around 0, no effect whatsoever. But you can pull together a couple of essentially existence proofs that you could find this negative impact effect of people moving from high tax to low tax states, but it's really not robust. Okay, so just wrapping up here. Different things can happen when we open the door to model robustness, but in conclusion, science has really traditionally been governed by a professional model rather than a market where people pursue their narrow self-interest. But competitive pressures have been building in science so that there's a sort of a growing spirit of capitalism in academic research, and the business incentive to publish is starting to decouple from the professional commitment to the production of knowledge. So the crisis in science is really about, whether scholarly research and the integrity of it can really be still maintained through professional ethics and academic self-governance. I think a big part of the solution is reaffirming the principles of Nellius and Verba, the conviction that science advances most when scholars can see for themselves. And the technology has never been more supportive of transparency. We frequently don't use it for the simple reason that we kind of don't want our work to be more transparent. And this is a collective action problem, which the individual incentives for scientists to make their work more transparent is just not very strong. So I'm really glad that we're here having this conference today, and I thank the organizers for putting it together because, I want to be proud of my discipline. I want to learn from it. I want the pressure to publish, to stay tightly coupled and connected with the goal of creating meaningful knowledge. And I'm optimistic that greater transparency will do that. So, thank you.